Okay, so I'm going to assume you had a crack at this problem, so let's go through the solution together. So before we do anything, we should figure out which variable should I induct over, xs or ys. So if we have a look at the definition of both concatenation, or the definition of concatenation, it looks like it's doing recursion on the first variable, so which indicates recursing over xs is probably going to make things work for us. So we're going to let this whole thing here, this whole statement here, denote p of xs, and I want to prove for all xs, p of xs. Okay, so the base case is going to be xs is equal to the empty list, so i.e. we want to prove p of the empty list. Okay, so we want to prove for all ys, the length of the empty list concatenated with ys is the same as the length of the empty list plus the length of ys. Okay, that's going to be our goal. So we're going to let ys be an arbitrary list, and then we want to prove this statement here. So we'll start from left hand side. Left hand side is equal to length of the empty list concatenate ys. Having a look at the definition of concatenation, empty concat anything gives you back that same anything. So you can just replace this with length of ys by a1. And then it's not so obvious where we can go from. So let's have a look at where we want to get to. We want to get to length of empty plus length of ys. We already know length of empty is 0, right? So I can always add in a 0, and that never changed the equation, so I'm going to do that. So this is the same as 0 plus length of ys by math. And then I can, in a sneaky manner, use L1 backwards to insert length of empty. So we can replace the 0 with length of empty. That's shocking. Length of empty plus length of ys by rule L1, and this term here is then equal to the right hand side of the equation. Okay, therefore base case is proven. Base case holds. Okay, so now I have to prove for the step case. So for the step case, we're going to assume p of zs holds for some list zs. Okay, I choose some zs arbitrarily. I'm going to assume p of zs holds. So what am I assuming? I'm assuming this whole statement here with zs instead of xs. So we're going to assume for any list ys, the length of zs concat ys is equal to the length of zs plus the length of ys. Okay, that's going to be my assumption. That's going to be my inductive hypothesis, denoted by IH. And what we want to prove under that assumption, we want to prove for any new element z, p of z cons zs. That is to say, we want to prove for all z, for all ys, all of this junk here. Length of zs concat ys equals length of zs plus length of ys. Okay, so this is what we've got to prove. So we'll do the proof over here. So we're going to let z and ys be arbitrary. And we're going to do the proof starting the left hand side and trying to get to the right hand side. So the left hand side is equal to the length of, I'm sorry, I've missed that term out. I've made a mistake. That should be z cons zs and z cons zs here. Sorry about that. Right, so we want to prove for all z, this statement's true if we put a z on front of zs. Okay? So the left hand side is going to be z cons zs concat ys. Okay, what can I do from here? Well, looking at the definition of concatenation, I can bring the first element out the front. So we're going to do that. So we have length of z cons zs concat ys by a2. And now ZS concat ys, this whole thing is going to be some list, right? So this thing looks like to the form Z cons WS, where WS is all this junk here. So if we look at the definition of length, the length of x cons xs is 1 plus what's left over, which is the xs. So I can apply the same trick here. This is going to be 1 plus the length of ZS concat ys by rule L2. Okay? At this point, this term here looks like my inductive hypothesis, so I can break it up. So you have 1 plus the length of ZS plus the length of ys. And what rule said I could do that? The inductive hypothesis said I can do that. And now I've got to somehow keep going until it looks like this. So we note length of, so here's the thing I want to get to. I want to get to length of Z cons ZS plus length of ys. And if we look at the length, the definition of length, 1 plus length xs is going to be equal to length x cons xs for any x. So I can be sneaky and group this term together. So I can put brackets around that. 1 plus length ZS plus length ys. It's probably a little bit overkill, but that's okay by math. And then I can use the length backwards on this term here. I can apply L2 backwards on this term, which is going to get me length for any term, any new element. I'm going to choose Z. So this term here is length of Z cons ZS plus length of ys by L2, and that's equal to the right hand side. Okay, so we proved it's true for the base case, proved it's true for the step case. Therefore we have for any list xs, for any list ys, all this statement here. So the length of the concatenation is the length of the first plus the length of the second. So therefore, by induction, the statement holds. And so it's always good to write at the end, write where your proof actually finishes, and then conclude it's true for all, it's true by induction.